Hey, welcome to our second video. How does the catalyst affect the rate of reaction? Hey, I wanted to mention something I forgot to mention in the first one. Please, 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 this week as you're looking over the assignment, make sure that you look at this right here. This reading, this collision theory reading. It looks like this. And there's going to be a couple of questions that you need to look at and talk about, why may they react? And we're going to talk a little bit today about the effect of catalysts on reaction rates. We want to make sure we understand that catalyst provides an alternative route for reaction with a lower activation energy. It does not lower the activation energy of the reaction. So these kind of things are important. The readings will help you. There's obviously diagrams. Pay attention to those. So what's a catalyst? Well, a catalyst is something that lowers the activation energy and it provides an alternative path. But what do we mean by activation energy? Well, you want to think of that as the energy required for an effective collision. There has to be a minimum amount of energy for things to happen. And, if we had a reaction between, like right here, a hammer and a nail, it's not spontaneous. It doesn't just happen. There has to be a little bit of energy to overcome the fact that they're like this. And that ability to lift up the hammer and add energy and then release that energy into the reactants and products allows the reaction to happen. Same with a match. So matches don't spontaneously burst into flame. We have to strike them. We have to add a little bit of friction, adds a little heat. That little bit of energy gets the whole reaction going, and then it'll burn, right? The bismuth salts will burn, the wood will burn. You've got yourself a flame. So it's the minimum energy required before a reaction can occur. Things don't just happen. Sometimes we got to give them a little spark. Think of that as activation energy. And when we look at our diagrams, whether they're exothermic or endothermic, and we'd always talk previously, like here in this endothermic change, oh, there's the enthalpy change. Or here in that exothermic change, there's the negative enthalpy change or the positive, right? This is uphill and they gain energy. This is downhill and they lose energy. But notice this has to happen with a little bit more energy. This is the activation energy. Reactants don't spontaneously turn the products. They have to overcome this little bit of energy in order then to rapidly turn into products. So activation energy is that distance between the reactants and the peak that we see in these diagrams. So activation energy is the distance between the reactants and the peak that we see. Got to put a lot of energy into this in order to get it started. Once it gets started, it'll go. So activation energy is a big idea, and it basically keeps things from spontaneously changing all the time because there's not necessarily all these little bits of energy around to cause the change. So a catalyst. What a catalyst does is it speeds up the reaction without being used up. Make sure you understand that definition. Catalyst speeds up a reaction without being used up. They work by providing an alternative route for the reaction with a lower activation energy. Think of getting a ball over a mountain. You'd have to put a lot of energy to get it up there, but as soon as it gets up there, it'll roll right down into the products or into the next valley. If you want to have a catalyst, to think of the catalyst as providing an alternative pathway. And that alternative pathway goes around the mountain, not over the top of the mountain. That alternative pathway then doesn't need as much energy to get to the other valley so that the rock can tumble down. So catalyst works provide an alternative route for the reaction, and that alternative route is characteristically having a lower activation energy. So what do we see? We see these. It speeds up without being used up, and it provides this alternative route. If we were going to do in this exothermic change without a catalyst, we'd have to put in more energy to get it started before it rolls down into the valley. With a new path, the energy path with the catalyst, there's an alternative route. Some of them still might go this way, but now they have another way. So more particles can go from here to here. And what we see then is an increase in the rate of reaction. Since more particles can go, more will do. A couple common examples. Maybe you have ever seen elephant toothpaste, Google that. It's a fun video. You'll see some stuff. Elephant toothpaste involves something very common you have at home, hydrogen peroxide. Probably have it in a medicine cabinet, and it's in a brown bottle so sunlight doesn't hit it. If sunlight hits it, it'll decompose even faster. I think it's UV radiation that causes it to break apart into water and oxygen. And if you wanted to, you can make it go faster even without that. You can use a catalyst. Manganese dioxide is a catalyst used in the elephant toothpaste reaction, or potassium iodide solution is a catalyst used in the elephant toothpaste reaction. And instead of this huge barrier being in the way of hydrogen peroxide turning to water, that alternative route has such a lower barrier, so many more particles can get over, that the rate of reaction goes really fast. And if you do an elephant toothpaste, you'll see what I mean. It's explosive. It's pretty cool, actually. Check that out. And that's a common one. Teachers sometimes demonstrate. Another catalyst that you're probably familiar with is your catalytic converter. It's inside your car, and it functions by taking your exhaust gas that has a lot of nitrogen oxides, carbon monoxide, and hydrocarbons, and it puts it through a catalyst. This catalyst is a solid catalyst, and it works by adsorption. And what this catalyst does is break these things down into a little bit safer, a little bit more manageable water, carbon dioxide, and nitrogen. These are a little bit more poisonous than this, though a lot of carbon dioxide is simply not good for our atmosphere. And inside that, it's a solid catalyst. And so what that means is the gases flow over this solid and they get to an activation site where they'll link in. And what the catalyst really does here is provide that alternative pathway. Typically, the solid catalyst will hold that particle in a perfect orientation for another collision. And so catalysts often provide alternative pathways by orientation. They tend to work on the orientation aspect of things. And if they hold it in a certain way, that allows this collision to occur more effectively and a new substance can form. That's another way that catalyst works. That's most often their alternative pathway. It has something to do with orientation. Hey, you guys, how does catalyst affect the rate of reaction? Speeds it up without being used up. It gives an alternative path with the lower activation energy so more particles can go. And what we see is just a faster reaction. Talk about those two things this week. Don't forget to do the reading and have a great week. Thanks for all your time. And we'll see you.